You're staring at a chemistry exam involving weak acids, pH, and equilibrium constants, and it's hard to know exactly where to begin. By the end of this video, you will know exactly how to set up an equilibrium table, calculate the constant of acidity, and determine the relative strength of any weak acid. To follow along, you just need a basic understanding of molar concentration, the standard pH formula, and a scientific calculator. This four-step calculation sequence provides a repeatable framework for analyzing the equilibrium of any standard weak acid solution. Step 1. Establishing the foundation. A weak acid is an acid that partially dissociates in water. The equation shows HA plus H2O yielding H3O plus and A minus. We track changes with a grid. At time 0, acid is Ca, products are 0. Acid drops by X, products gain X. Combining these gives the final equilibrium state. Acid is Ca minus X, products are X. This grid maps the entire chemical reality of the solution at equilibrium. It provides the structured blueprint for all the math that follows. Step 2. Plugging in our variables to solve the problem. A test question gives you a solution with an initial concentration of 0.01 moles per liter and a measured pH of 2.9. First, verify it's a weak acid by checking if the pH is greater than the negative log of the initial concentration. The negative log of 0.01 is 2. Since 2.9 is greater than 2, it's confirmed. Now look at that variable X from our equilibrium grid. That X represents the final molar concentration of hydronium ions in the solution. We can calculate the exact value of X using the inverse log of the provided pH. Type 10 to the power of negative 2.9 into your calculator, and you get 1.25 times 10 to the negative third. By isolating X, you translate an abstract pH measurement into a concrete molar value that you can plug right back into the grid. Step 3. The constant of acidity, Ka. It is the ratio of products over reactants. We replace the symbols with algebra, x squared over Ca minus x. Inserting our numbers gives the x value squared, divided by 0.01 minus x. There is an approximation shortcut you can often use here. If the resulting constant is less than 10 to the negative fourth, x is considered negligible in the denominator, and you can omit it to simplify the math. Running the calculation yields a final Ka value of 1.58 times 10 to the negative fourth. The resulting Ka value is a constant. It quantifies the specific ratio of ionized products to reactants, defining exactly how this acid behaves in an aqueous environment. Step 4. Determining relative strength. Comparing tiny exponents like 10 to the negative fourth is difficult to do at a glance, so chemists convert the Ka into a much simpler number called pKa by taking the negative log of the Ka value. Taking the negative log of the constant we just calculated gives us a clean pKa of approximately 3.8. This chart plots the pKa scale, organizing bases on the left and acids on the right. Look at the absolute bottom. At a pKa of 0, we find H3O+, the strongest acid. This sets the rule: the lower the pKa value, the stronger the acid. To test this, let's compare our acid, which has a pKa of 3.8, with another acid that has a pKa of 4.75. Which one is stronger? Following our rule, the acid with the 3.8 pKa is stronger. The pKa operates as your primary comparative metric, allowing you to quickly rank the reactive strength of any weak acid against another. You have just systematically solved a multi-stage physical chemistry calculation from scratch. You constructed the equilibrium grid, derived X directly from the pH, calculated the constant of acidity, and determined the acid's strength using the pKa. Here is the entire mathematical sequence fully laid out. Grab a screenshot so you have it ready to review. You can apply this exact same logical sequence to weak base calculations as well. You simply substitute the Kb formula in place of Ka. By internalizing this core four-step framework, you have the necessary tools to accurately dissect and solve any weak acid problem on your next exam.